The last one, hopefully you've been able to go and press the button to get things to happen and take a look at things in the viewer. You can also sort of keep clicking as we sort of go and move on. What we're going to be going and talking about now is a fairly important part of the process, and this has to do with coming up with the risk numbers, okay? And what we've done up to this point is to go, and if you remember, we predicted how things should look. We've gone and can go and see how things look. There was sort of a magic button that you pressed that said calculate probabilities. I didn't tell you at all about what was going on behind the scenes. And in this lecture, I'm going to tell you more about what's going on behind the scenes and talk about a couple additional caveats or things that you should consider associated with that. So if you just give me a quick moment here, I'll switch over to the laptop and jump to the next presentation on risking, lecture 10. As you can see, this is one of the shorter lectures, and but again, I think it's one of the more important lectures because I think that a lot of people have sort of questions and are involved in this risking process. And I think no matter who you are, whether you're a specialist or asset team member, I think understanding the ins and outs of this spreadsheet, how it works, and having sort of ownership of the results that comes out are going to be a very important thing. Okay, and let's sort of start with what these humps really are that we ended up calculating. Okay, and what these humps are is that they're a conditional probability for those of you who like to think about these things. But it's that given that we have a brine sand underneath a shale, what is the probability that we'll have a certain amplitude or reflection coefficient? Or in other words, as a function of amplitude, what is the probability that we would have that one particular amplitude? As you can see here, that the most likely value for a brine would be this value. This is still pretty probable. This is not very probable. Okay? Okay, this is the conditional probability that if we had a gas, what would be the probability of the amplitude? Again, you see the most likely value for gas is here, but this is still modestly probable. This is not very probable at all. Okay? And so that all of the stuff that Dave went over and all these different formulas, and when you went into that rock physics spreadsheet, the result of it was to get these important conditional probabilities. Okay? Now, there's a particular problem here, and let me just go back for a second, because what do we really want to go and find out? Okay? Well, we've just gone and extracted an amplitude, and so we want to know what the probability is, given that we've seen this amplitude, that we have brine. Okay? Does anyone see the problem here? The card, yeah, it's in the wrong order. Okay? We have to flip the order of this conditional probability. Okay? And this is where you come about with Mr. Bayes, and that's the name that you hear me use a lot, to the point that you may think it has to do with some religion from time to time. And it's actually kind of interesting. There actually are two different perspectives with respect to statistics, and people really believe in them, and you're either from one school or the other. So it ends up being sort of close to which particular school you are in terms of statistics. But anyways, these are in the wrong order, and we need to go and come up with a commutation relationship. Or in other words, we need to go and find out what the probability is given an amplitude that we end up having gas, okay? And if you go, and the easiest way to go and derive this is to write up the joint probability in terms of this, and then sort of looking at it flipped on either side. But I'm just going to go and show you the result of it and sort of explain what each of these particular terms are, okay? Okay, this is what we want to find, okay? Okay, what do we have? Well, we have this number right here, which is the probability in the wrong order of gas. We also end up having the one for brine sitting down here. And then we just have a probability of gas just sort of chosen from the population, okay? I mean, what do you think of the, who tells us this about this probability of gas? Do you have any idea, Deborah, or? Well, you do. Yeah. It ends up being, and when I sort of say that, it is actually the natural place for the inclusion of the geologic risk, okay? That this is the probability of having gas before you look at this information contained in the amplitude, okay? There's a probability of gas here, there's a probability of brine here, and if you only had two things, this would be 1 minus the probability of gas, okay, beforehand, okay? The parlance that you'll hear us use from time to time, we call this the prior probability. To really think about it in terms of this is where geology and petroleum systems comes in to modify things, okay? And then it ends up coming, then the results of the remote sensing end up being added here, okay, in terms of this term, okay? Also notice the way that this particular formula goes. You have the probability of gas times the conditional probability in the wrong direction. Then you have a sum of all these bits on the bottom. You have the probability of gas plus times the conditional probability, the probability of brine times the conditional probability. And if you have more cases, like you have low saturation gas or you have oil, you just keep on adding pluses here, okay? Whenever you want to go and find the probability of oil here, you just have to replace this gas here, right here and here with oil, and then have the sum of everything on the bottom, and you end up having the right answer for any one of your constituents. I think you can see that the sum of all the probabilities then, since this is the common denominator, if you sum them up, they end up summing up to 1, okay, with this formula.
You include other things like, say, coal in that?
Yeah, good point.
So in the Falkland Islands case, that wasn't really included, was it? So.
That is correct, yeah. And that would just be one more case, you know. What's the probability of it being coal given that amplitude? And it's one more thing on the list.
And that's a very good point, and goes back to a point we made earlier in the trend curves business. If you have omitted something that's possible in your analysis here, it's not in the denominator, then you include no term in the numerator to assess that possibility. It might have a distribution that looks just like oil, for example. Okay, so and it might have a probability that's much smaller, but if you have omitted it altogether, you'll never think about it. You'll never assign any probability.
And also, I mean, you were asking earlier about porosity, right? Well, you can just go and have a probability of high porosity given that amplitude, and then there'll be the probability of having that high porosity just from your considerations of the geology. Then you need to have the conditional probability of having that amplitude given high porosity, and then the equivalent of brine could be low porosity, okay? And you just go and do your calculations. I mean, I think a straightforward generalization of it, okay? Okay. But now let's go and ask, okay, what does this really mean? And we can sort of think graphically about it. And if you go and say that we have an observed amplitude, and this is the amplitude that we've observed, and we look right here. First of all, the probability of the amplitude given the gas is going to be the height that we're looking at right here. And the probability of the amplitude given the brine is going to be the height of that hump at this same location, okay? Now let's take a look, and for right now, let's assume that the probability, prior probabilities or geology tells us that gas, and petroleum system tells us that gas is as likely as brine. So all these things are the same number, and they end up dividing out of the equation, okay? And so let's ask, okay, that, you know, what ends up happening, or sort of what is this formula, okay? Well, the formula for gas is just going to be the height of this in the numerator, and in the denominator is going to be this plus this, okay? So in this case, where this is smaller than the sum, this is going to be a fairly small number, okay? If I was asking for the probability of brine, this would be in the numerator, the sum would be in the denominator, and that would be a number that would be fairly close to 1. And as we move out here, where the particular height of the gas goes to 0, we have 0 in the denominator, and this big number in the numerator, 0 in the numerator, this big number in the denominator, so you get 0. And if I moved over here to where it had an observed amplitude that was sitting where we ended up having, where the gas would be very large and the brine would be very small, we would have the same large number in the numerator and the denominator, and ergo we'd end up having the probability of gas would be coming close to 1, okay? One other thing, though, to note about this, if we say the probability of gas is 1 and the probability of brine is 0, okay? That means this is 0, this is 1, the numerator is the same as the denominator, and the probability of the gas is always 1, okay? So that if you start off with a high prior probability of gas and have it as 1, you end up getting that as an answer sort of coming out. And the closer this is to 1, the harder it is to pull it away from that, but also the smaller effect. If it's already 95%, no matter what you do in terms of your observation, even if it is a favorable observation, you can only move it from 95% up to 100%, so that that particular measurement isn't going to have a lot of effect on it, okay, or on the probability. And so it has sort of the right sort of saturation characteristics.
Hey, Mike, before you leave that slide, let me make one other point. I want you to consider briefly what happens if all of these humps, the same picture, if all these humps get much broader. We talked about reducing the uncertainty when you can. That's important. And Mike talked this morning, I think it was this morning, when you went over the exercise that you showed the tornado plot, and reduce it where, you know, starting from the biggest things, and when you get to where you can't reduce it, don't waste your time anymore. That's efficiency there. But what happens is obvious. There will be a large region in which you don't get much discrimination. These things have about the same, these bumps, these two arrows have about the same magnitude. And only at the ends will you get, you know, significant difference. So that's why we preach, reduce the uncertainty, reduce the uncertainty. That's what it's all about.
And in fact, I hopefully, if you go, those of you who can sort of stop looking at the manual, I sort of want you to go through and sort of think about in your own mind what's sort of the answer in these particular cases, okay? And I think it's sort of good to go through this mental gymnastics, and actually will demonstrate something that that Dave was saying. Here I show a brine and a hydrocarbon peak, and I show an observed amplitude. And I asked the question, is it likely, and assume that we sort of have equal probabilities, is it likely to be brine or hydrocarbon? Or is it uncertain, okay, to be able to tell the difference between the two? And, in this particular case, it's not certain because the size of the stick for both of these are equal, even though it's small. And so you would say that this is a not certain case, okay? And so now let's go and assume we have the same two humps, but now we end up having this as the observation. And what would it be in this case? What would be your prediction?
Certainly brine.
Certainly brine. That's okay, correct. Okay. Okay, now we go, and this is the way that things are displayed out there. And Jack, what would you go and say in this case?
That's brine.
Like there's certainly this is, I'm sorry, this one right here.
Yes.
I'm sorry. Certainly gas. Okay, now we have things, and this is what Dave talked about, is we have these things that end up having they end up being peaks that are much, or humps that are much thicker, okay? We haven't been able to reduce the uncertainties, and we've ended up going and having broader conditional probabilities, okay? And this is what we ended up seeing, okay, is the amplitude sitting over here, okay? And in this case, Ian, I mean, is it certainly brine, certainly hydrocarbon, or maybe brine, or maybe hydrocarbon, or you don't know? Okay. Well, is there any preference whatsoever? I mean, is it 50-50, or is it pushed one way or the other in that case? Okay. If you had to go and say, which one would it be? Was there a modest preference for two? Very modest to gas. Yeah, that's right. Okay? And you would see that there wouldn't be a lot of push, but it would just go, okay, maybe gas, okay? Just sort of pushed a little bit towards that side, but you're right. It'd be hard to tell. Okay? Okay, in this particular case, okay, John, what would you say the outcome would be?
That's maybe brine.
Maybe brine, okay. Okay, now, okay, there is an interesting case here, and you'll say, because many times people will say, well, because there's overlap, you can't tell anything. It will always be maybes, okay? Okay, Guimin, is this a maybe?
This looks like certainly gas.
Certainly gas, that's right, okay? And this is something to remember, is that if you go and look at particular areas, that there ends up being, even if there is overlap, if you end up getting out on the wings, that you can actually, even let's say in a very good sand, that you can see an amplitude that's so bright that it really has to be a gas sand, okay? And this is something that does happen practically. And it also does, I mean, it's sort of something that's sort of surprising, but if you go back, that it actually has sort of some ways you can sort of touch this sort of statistical phenomenon, right? One is, let me pose it this way, okay? If I was going into a new society and wanted to go and tell whether or not that population had, let's say, of shoe size that was sort of fractionally different by, let's say, a quarter of a shoe size in another population, what would be the easiest way to say that there was a difference, a small difference in the shoe sizes of the two populations?
Look at the maximum value.
Look at the biggest shoe size you could find in the two populations. And that's the equivalent of what we were going and looking at here, is that you end up seeing there are small differences in the average can have big differences in what the extrema are, okay, of those. And to sort of keep that in mind when we're sort of looking at things, that the brightest amplitudes we can see, where we really have good rocks, okay, can actually tell us and can give us a clue an important clue about what is actually there.
So Mike, in that case, if you're far enough to the right, you can probably say that your model though is
Right, that's an
incorrect.
important point.
That is correct.
That's a
yeah.
very important point.
Yeah. That is correct, yeah.
If you get something that's way off the end of what you expect in any of your possibilities, it means you either made some kind, likely, you either made some kind of mistake in your seismic measurement, or you made some kind of mistake in what you anticipate, in the spectrum of possibilities you anticipate.
Yeah, but there's also, I mean, right here, I sort of purposely showed this, because this is probably about 5% probable. And that if you go and look at, and it's sort of the vertical to lateral sort of theorem, weak theorem. So if you see vertical sort of changes, you also will see sort of the same distributions of changes laterally. And so that what I'm pointing to here, that if you could go and find this sort of 5% corner, that you normally, if you look around in an aerial sense, will see about 5% of the area that will have this. So it's probably something that you can't identify. What Guy is sort of talking about, this gets down to 1% or less, I really would start becoming concerned about something being wrong in my analysis, okay? Probably once you just go, if it's 5 minutes, it's probably a good time to go and switch. This is our risking spreadsheet. And I'm going to go through each of the particular parts of the risking spreadsheet. Okay. The first part are the geologic inputs. You'll see that they're divided according to the common risk elements. What's the probability of reservoir? You talk to stratigraphers a lot. You look at the character of the sizes of the bodies. And that's what I was asking things, the questions of you, Ian. What are the shapes that you expect of a coal body? And many times we'll look at shapes and sort of vertical sequencing in order to get an idea of whether or not it's likely to be a sand. I was asking questions that are aimed at, is it likely to be a coal? In fact, it was trying to understand the prior probability of coal from geologic considerations for the Falklands area. What's the probability of a trap, okay? I mean, is there a robust structure there? Does it look like we end up having sort of stratigraphic trapping elements? That's looking at more of the geometry, okay, of fault networks and the like associated with the seismic. The probability of seal, okay? That is, about whether or not there's a rock on top that can seal it, whether or not if there's a stratigraphic boundary or a fault, can that actually seal things. The gas seal multiplier comes about from many times. Can you seal the amount of gas that you expect? It's hard to seal gas because the capillary pressure with a particular column ends up being greater. What's the probability of having a thermal charge? Someplace we have to have a good source rock. It's had to get hot enough to be cooked. And that needs to then, or source migration timing. In other words, you have to have a source, you have to be able to cook it, you have to be able to migrate it to where the trap is at the proper time. And that's a common risk element that we do through petroleum. The next thing is, if you've gotten it there, is it going to be preserved, okay? It turns out that if you're too shallow, if you're not warm enough because you're too shallow, certain bugs can live that like eating hydrocarbons. But the problem is that they actually poop tar. And so they eat oil, poop tar, and it's, it ends up being what we call biodegraded, okay? And so that is a particular probability. We can associate that with how long you've been at these sort of low temperatures, okay? The next one is what's the probability of having gas versus oil? The prior probabilities of that come from looking at regionally what are the probabilities. It also is associated with the type of source rock and how much you cook that source rock. Because if you cook it too much, it's going to be gas. You gotta sort of cook it a little bit, but not a lot to have it be oil. Other sources tend to be more gas prone than others, depending upon the type of source rock that you're dealing with. what's the probability of biogenic charge? Well, it turns out that these bugs that actually like to eat oil not only poop tar, they poop gas, and so that you can end up getting biogenic gas, okay, that end up going, and actually that can be significant, and it turns out that it's actually a fairly nice dry gas, okay? And so that's where this particular probability of biogenic charge ends up coming from. But you also have to worry that this biogenic charge can also be incomplete if the bugs poop a little but not a lot, because they have to reach a high enough local saturation to be able to overcome surface tension and to start moving around, okay? So I probably have given you the poor man's tour of what our risking is about and where these numbers come from, okay? And why do we want these numbers? Well, there are fairly simple ways these can get divided up into the probabilities of each of the things that we can tell. Low saturation gas, oil, shale, and I'll talk about that a bit and actually point you to in the spreadsheets where you can see those formulas, okay? And so this is where you fill that out. Most of the case we deal with one interface, and you can either have AVO or not have AVO. And we also bring in other pieces of information. One is going to be structural evidence, and I'll talk a lot about that in a second. We've been talking about seismic reflections. You can explicitly bring in seismic imaging velocity or spectral decomposition as additional Bayesian boosts. We've actually kludged it together and sort of used multiple spreadsheets and take the output of one as the input of the next and use the seismic imaging velocity area in order to be able to kludge up the control source E&M boost. But that could just be added in. But one thing that ends up being fairly important, and I think is a problem why other companies have had problems getting good look-back calibration, comes about because we always think, or if you think that you know everything, you actually forget about stuff. No matter how hard we try, we always overlook something, okay? Or the data itself cannot be processed, let's say, as well as what we think it can be. And so we end up having a particular probability that all of this analysis we've done is correct, okay? I've taken everything into account, and that's 67% here. But what I'm saying is that 33% of the time, I've made a mistake. I've forgotten about a cold, or I've not gotten my trends correctly, or my well-processed seismic data isn't processed as well as what I think it is, and I should totally ignore all of the analysis that we've been doing and just live with those geologic priors, okay? And so it's really a frontal recognition that we screw up, okay? And how can we determine whether or not we screw up or not? I got together first with Gary Grubitz and later with Richard Keene. We really sort of put together and came up with some particular questions that you can go, and I think in a fairly reproducible way, answer. That has to do with well data context. You know, do I have numerous wells that are interpolated? Do I have a few wells extrapolated? Or am I coming from, 300 kilometers away in terms of my well information? And if I'm doing this, I'm much more likely to have the right trends, okay? The well data type, do I have all the data I need, or do I only have a little? Am I having to fudge it? The more I have to fudge it, the more likely I am to be making some mistake. Fluid data, okay? Do I have relevant fluid data, or am I just picking numbers out of thin air, okay? Seismic data type, okay? Do I go and have, sparse 2D? Do I have, spec 2D? Do I have spec 3D? Do I have good quality, sort of gold standard 2D? Or do I have good quality, gold standard 3D data? And then if I look at the data quality, do I have absolutely crappy subsol data where I can barely see reflectors? Or do I have nice, crisp data that ties my wells to within just a few percent, okay? And you go and you set these particular buttons accordingly, and it's a simple linear formula. I go and I encourage you to click on here and see what the formula is and how it works, okay? And given where you set these buttons, you come up with a number that's, okay, sitting here. I'll tell you, we don't allow this thing to go to 100%. It's hard to get it above the number that you see right now. Also, I ended up going and I think people around here really started playing with this at first. And they ended up coming up, after they played with all the numbers, they ended up realizing, you know, it makes a big difference on whether or not it's spec 3D or reprocess 3D. And it also makes a big difference on whether I'm poor or good quality data, okay? And that's really not, you know, a particular sort of accident that it comes out that way. Jeff?
Is there a certain number, size of confidence drops below where you don't proceed with your initial boost? When you get to 30%, you still go through the process?
Well, I mean, you can go, and if you get below 30%, you're never going to move it very much, okay? So you can probably go and say that you would, at that point, you know, you're not going to have a profound effect, you're not going to get very large boosts, and you may well go and say it's not worth the effort, okay? But also the thing that's kind of nice about it, you can say if we go and reprocess this 3D data, move from here to here, does that make a substantial difference? Are the boosts going to get large enough to matter? And so there's a nice way of where we can go in now and do a value of the improvement of the seismic data, or the value of the acquisition of particular well logs. Okay.
So I presume that's the formless.
Was that?
That's the formless case too, where you went from your spec 2D seismic to your reprocess.
That's right, and we went from you know, sort of this point up to this point. Okay. You know, also, you know, we've done it like in the you know, in South Africa, the case you'll be looking at. We initially were sitting down here, you know, with respect to, you know, sort of spec quality 2D, and we ended up going all the way up to good quality 3D. And could go and say, what would things look like? How large could the boost be? And that ended up informing whether or not we would acquire the data.
How did you determine the coefficients in this linear formula?
Experts, I mean, you know, and I think that it's sort of where the comfort factors were. You know, how much would you like to trust that data if you had this type of input? We originally sort of tried to design some fuzzy logic, and it was really over-engineering. And we ended up deciding to use a simple linear formula. And we just had Richard Keene, myself, Gary Grubitz, people with a large amount of knowledge come in, change the bars around, and then get comfortable with what the particular responses were associated with it. We recognize that there's a large amount of potential miscalibration. As it's turned out that the calibration of this stuff has been on, and so, you know, all you can do is try your best with your experts and then look back. But when we talk about the interpretive components of this, this is you know part of where we tried. I sort of call it semi-quantitative. We will try to make sure it's reproducible, but it really comes from sort of answering certain questions. And the people that haven't put in these type factors have found they've had fits trying to compare things because they always are surprised, you know, and they don't have that explicitly in their methodology. Okay, and then you also put in what the observed reflection coefficients are here for the near and far. So a fairly straightforward number that comes from your amplitude extraction spreadsheet where you sort of pick things in the target level. Okay, we have another thing that has to do with fit the structure and what's the strength of it. And there are sort of three positions here. One is I don't expect to see any evidence, and I don't see any evidence. Another one is I really expect to see evidence, but don't see any evidence. And I expect to see evidence, and I really do see the evidence. And also there are three different types of evidence or four different types of evidence, going from sort of weakest to the strongest. And they all have to do, though, with the fact that gravity causes light stuff to be on top of heavy stuff. The first is fit to structure, and I'll talk a bit about that more. We've already said a bit about it. The next thing is seeing a feather, and I'll describe that. A flat spot, and then a double flat spot. And that we've gone and over time, we normally have not gone and ever said anything sort of much past here, even if it's a double flat spot. And that accordingly, with these things, we've sort of come back, and and I think in the end, we've always tried to get, at least as a portfolio, make sure that when we go and have things in the right ordinal level in terms of fit to structure, which goes up to about here, and then to come up to sort of this level, you end up having to have these other pieces of evidence, okay? And we sort of talked about it, okay, that, first of all, you see here, this is what we would end up calling feather. You have something coming down, and then it ends up having a feather, or you have something cut across the particular sand, and you have a feather zone. And again, you end up seeing some evidence of this feather here and feather here. This is what we call fit to structure. You look at structural contours, and you see this particular amplitude cut off at a common contact.
That's a time map?
No, that's depth.
That's depth.
And I think where we talked about before was this is 50% net to gross potentially. This is 50% net to gross. This is probably 100%, but it's the same fluid as this. And we talked about that at the time. We didn't have this picture up, and I want to sort of go and sort of remind you of that. And so, this is what we mean when we say sort of fit the structure. When we go and sort of talk about, overall sort of flat spots, we really are talking about something that really has sort of extensive over many different layers of where you can literally see a large amount of what is obviously flat with stratigraphy that's going in the other direction, okay? And many times people will look at sort of optical smashes in order to be able to see that. And also, in this case too, that you would go and say here that there's a particular possible feather at this case, and also another amplitude in another level that goes and possibly changes at the same level, with also another change in amplitude in two different layers at the same location. And then once you go and set all of this, that first of all, from the geologic priors, they get split up into things like gas, oil, degraded oil, low saturation gas, brine, and shale. And I'll go and show you quickly when you start the exercise where you can see these formulas of how things get split up. And then we go and show this pictorially as our wheel of fortune from just our geology. And then you can go and click on the different pieces of evidence or click them off, and you'll see the way that these sort of wheels end up changing. And it's just a simple application of Bayes' formula, and we end up doing this in a sequential way, and you end up getting what the probabilities are coming out the back, okay? And for those of you color-wise, gas normally is shown as red, oil as green, Degraded oil, since it's tar-like, I show as dark green. Low saturation gas, since it's a little bit of red, I show as pink. Brine is blue, and shale ends up being the sort of the muddy color. Okay, what should you go and sort of remember out of this? That this Bayesian method combines geologic risk with seismic AVO, structural fit, seismic imaging velocity information, and potentially CSEM information. And that the seismic confidence factor is an important part of this combination. And really, the particular methodology of using Bayes would not work if you did not recognize that you were wrong some of the time. Okay, with